All right, well, why don't we get started? It's my pleasure today to introduce our last speaker of the calendar year, who is Hannes Bernien, who's an assistant professor at the University of Chicago. Prior to that, he was a postdoctoral fellow at the Harvard Quantum Optics Center and had his PhD from the Technical University of Delft. I'm very excited to hear a lot of the exciting work on dual species quantum processors and quantum network science coming out of his lab, and I want to welcome everybody here today. Just as a reminder, we'll be pausing for questions throughout the talk, but if you have thoughts as they come up, please feel free to use the Q&A. We'll use that for all the questions for the Zoom participants. And if you're watching on YouTube, you can also use the live chat to enter your questions. So with that, again, thank you to Hannes for joining us today, and feel free to take it away.
Okay. Yes, thank you very much, Lindsay. It's really wonderful to be here. VAMOS is a really special seminar series, kept me going throughout the pandemic, and it's really awesome that it's still going on. And I'm really excited now to tell you about our research at the University of Chicago. You can actually see a little snapshot of our research here in the background. So what we like to do is to build large quantum systems from single atoms. So each bright spot you see here in the background is a single atom. And you see there are two colors, and I will tell you why there are two colors. But for now, what you see is basically that we have a lot of control of these atoms where we put them. We can put them into these regular grids, or we can even spell out the name of the seminar, VAMOS, here in single atoms. And for the experts, this is rearranged atoms, and this is a single shot. So I'm going to tell you all about how we do that and what we do with that. But before I do that, I want to zoom out a little bit and actually even step a little bit back in time and take a historic perspective. And I do that with this slide that I took from Chris Monroe. I asked him for permission, so this is not stealing. I just want to highlight here his slide from a talk that I think I've seen maybe at the beginning of my PhD, and it actually made me really excited and really motivated for this kind of research. And in this slide, what he does is basically give an overview at that time of different implementations of quantum computer architectures. At the top, he has individual atoms and photons with ion traps, of course, at the very top. And I think this is rightly so. At that time, ion traps and maybe still are really one of the most promising platforms. But also that time already, there were a lot of research efforts on solid-state systems, superconducting qubits, semiconductors, and also defect centers in solids, or maybe dopants in solids. What Chris actually did, he characterized these systems into two categories, into systems that scale, so these are the solid-state systems, and systems that work. And it's actually I mean, it's kind of funny to look back at this and think about what all has happened. And actually, if you look in this category of the scaling systems, you now really see how these systems really start to work, and work actually really, really nicely, maybe with superconducting qubit chips with tens, maybe close to 100 of qubits. But at the same time, you also see how these systems that already worked maybe a little bit earlier now start to scale really, really nicely. And this is where I'm really excited. We've seen a lot of progress in recent years. And actually, there's one more, I would say, architecture that maybe Chris didn't consider at that time yet, but that has gained a lot of traction. And that is what my group is also working on. And these are arrays of individually trapped neutral atoms. So this is a little bit different from optical lattices. Here, actually, we use tightly focused laser beams to catch single atoms. And we can use an array of these laser beams to catch a large array of atoms. Actually, all of these atoms, they will be the same. So in some sense, I would say it's the ideal building block now to build large quantum systems. And just kind of to give some examples of this scaling, here is an example from Antoine Brouvet's group, where they use these arrays in combination with Rydberg excitation that I will talk about later to do quantum simulation of quantum magnetism with hundreds of rubidium atoms. It's also really interesting to think about these quantum simulation problems maybe from a different perspective and think of them maybe more as optimization problems for maybe computational complex problems. This was investigated by Misha Lukin's group, with also a few hundred atoms, investigating maximum independent set problems. And then actually, if I look now at these atoms more as qubits, I can find really long-lived hyperfine states or maybe nuclear spin states that give me very long coherence times. And here's just some recent examples from Jeff Thompson's group, Adam Kaufman's group, and also from companies that are now in this space where they use nuclear spins to show second-long coherence times and even maybe tens of seconds of coherence time. So you have very good qubits, you have many of them, and now you can also make them interact, what I already said, by exciting them to these highly excited states, Rydberg states. You can use that maybe in this quantum simulation context, but you can also use it now to perform gates or entangling operations between the atoms. Here's a really nice example from Manuel Andres' group, kind of highlighting the progress in these entanglement operations, where we now have high fidelity entangling operations with maybe 99% fidelity and higher. So now groups are really kind of taking all these ingredients and putting them together to run algorithms, for example, with individual addressing. Here an example from Mark Safman's lab from earlier this year, where they are now really compiling quantum algorithms on these architectures. And slides like these nowadays are really, really dangerous because, of course, I have forgotten many or haven't highlighted. So there's so much work now in this field. And here I'm just showing you two recent reviews that I really find really well written, and that I always recommend to people that are starting in this field to start off with these two reviews. So now I'm telling you, so now I'm basically saying we have these qubits, they're very long-lived, we have very good entangling operations, but there's actually more to the story. I think that these neutral atom arrays, they are not just your usual maybe quantum processor implementation, but they actually bring something special to the table. So there are a few properties that make them really special. For instance, these Rydberg interactions, they can be rather long range. By choosing which Rydberg state I excite to, I can be in situations where I maybe just have nearest neighbor interaction, or I can be in situations where I can have interactions beyond nearest neighbor, next, or next nearest neighbor. In the quantum information language, that would mean I have very long connectivity. At the same time, I don't want all the atoms to interact at the same time. So if I choose maybe these high-lying Rydberg states, I can't do as many gates in parallel. So there's an interesting trade-off between parallelism and connectivity, I believe, in this platform. Another really unique feature is that if you excite not just a single or not just two atoms to Rydberg states, but multiple atoms, you can actually get access to native multi-qubit gates, such as a Toffoli gate that you can just get by exciting 3 atoms to Rydberg states. Whereas in other architectures, you would maybe have to decompose it into many 2-qubit gates, maybe 6 CNOT gates, if you just had nearest neighbor interactions and not these native multi-qubit gates. So together with my colleague Fred Chong in the computer science department, who thinks a lot about how can I efficiently compile quantum algorithms to architectures, we were asking, can we leverage these 2 unique features in efficiently compiling quantum algorithms, and how would these hypothetical atom array processors then perform? So what his group did, they set up basically, they wrote a compiler, and you can actually download that compiler, and they benchmarked it on a 10 by 10 atom array where they were just considering a single and 2-qubit gates. And in the first kind of set of numerical experiments, they were investigating, can we leverage this longer range connectivity? So here they took typical, I would say, benchmarking algorithms, such as the Bernstein-Vazirani algorithm, and they were seeing how many gates do I need to implement it for different problem sizes, independence of this interaction distance. And maybe not too surprisingly, you see how the gate count basically drastically decreases as you increase the interaction distance. And this is here for the Bernstein-Vazirani algorithm. This behavior they also saw for maybe for these controlled multi-unitaries or different addition algorithms or QAOA, so a whole suite of benchmarking algorithms. We saw a big reduction in gate counts. But of course, we have this trade-off between parallelism and maybe a gate count. So the question is, does the algorithm also get shorter? So here they also looked at the reduction in gate depth, and they saw that also these circuits, they do get shorter. So yes, you can win by increasing the interaction range, But there's also an interesting feature that you don't kind of continue to win with this interaction range, and it actually informs us on how should we build these quantum processors on atom arrays, maybe choosing interaction range where we have maybe 3 to 4 sides interaction range. So this was the first set of numerical experiments. In the second set, we looked at what happens if we also add these native multi-qubit gates. And here for, again, 2 benchmarking algorithms, this multi-controlled unitary and this addition circuit, you see how the gate count reduces. So you are actually comparing the dashed line to the solid line, dashed line without the multi-qubit gate, solid line with the multi-qubit gate. You see a drastic reduction, and that is both in gate count and also in circuit depth. Maybe not too surprisingly, but really nice to see, and really, I would say, puts a very positive prospect on these atom array processors that they can really offer something unique here. So I'm see myself making a very strong pitch for atom arrays here. You have wonderful qubits, very long-lived, and you have all these unique opportunities. But I really want to tell an honest story here, and I also want to tell you about the challenges that we face that are also quite unique to this platform. And here's just one example list. I think there are maybe even more challenges, and everybody might have their own list, but here's my list. And right at the top of the list, I have measurements. Measurements here in this architecture tend to take a rather long time and also be very destructive. Typically, we do qubit measurements by performing state-dependent loss. Basically, we throw out the qubits if they are in one state, but keep them in the other, and then we do a fluorescence image. Of course, this takes a long time and is very destructive. Atoms also do tend to get lost over time, maybe due to background pressure, so that's by itself a challenge. Another challenge, or I would say kind of a general challenge, is that we actually spend most of our time just making cold atoms, trapping them in tweezers, and doing all these things. And the least amount of time we spend typically on executing our algorithms. So there's a huge imbalance here. And also, I think a very big challenge for the whole community is to individually address qubits in large arrays of atoms. And to address some of these challenges, what my group here at Chicago is doing is that we follow this dual species atom array approach. And that's what I want to tell you about in the next part of my talk. So a little motivation on this efficient compilation, but now we get to the hardware side and how do we trap these single atoms and why maybe 2 colors of atoms add unique benefits. So, and then actually, okay, here's an overview. In the next part of the talk, I will show you one specific example where we really show some, or where we see some big advantage using this dual species approach, where we perform actually mid-circuit readout of one species and use that to correct errors on the other species. And then in my final part, I actually want to zoom out even further and not just scale the number of qubits, but actually scale the separation between the qubits and tell you about our research efforts on quantum networks and quantum network nodes that are suited for really long distance entanglement distribution. Let's get started here in the second part, and I'm starting by showing you a little sketch of our setup. So we, of course, have ultra-high vacuum chambers. We use high numerical aperture microscope objectives to focus our tweezer light into these vacuum chambers. We shape our trapping arrays by using spatial light modulators, and we have separate trapping wavelengths for rubidium and for cesium. So we can independently create these trapping arrays for rubidium and for cesium. And then, as many of you know, there's one challenge when you trap into these optical tweezers, and that is that they will be kind of randomly trapped in random positions. But then we can use this acousto-optic deflector basically to pick atoms up and put them into their designated spots. So it's kind of this combination that is really popular now in the community, where you have one device to perform, basically have this static trapping array. In our case, it's 2 devices because we have 2 species of atoms, and you have a device that can quickly sort these atoms, in our case, an acousto-optic deflector. So this is just the sketch of the setup. Here you see an image, so it's actually not lying down, it's basically upside down. our atoms start here at the top. This is our rubidium cesium 2D mod, our atom source. And then we push the atoms down here into our 3D mod region. You also see these high numerical aperture microscope objectives there. And that is where we perform our experiments. So let's perform one such an experiment. So let's just shine in the 2 SLM lights here, trap atoms and take an image of it, or take multiple images of it. And then this is what we see. So this is our dual species array with 512 trapping sites, about half of them being cesium atoms in yellow and half of them being rubidium atoms in blue. So when you see a nice picture like this, you should always be a little bit skeptical. It's maybe a little bit too nice. And indeed here, actually, what we have done is we added a few single shot images together. But I don't want to hold back anything. So here's a single shot image. And you see actually in a single shot image, we also get a very clear signal if we have an atom or we don't have an atom. And if we analyze these single shot images, we see that we have about 50 to 60% loading efficiency, both for rubidium and cesium. And this is actually quite, or for us, it was quite astonishing because we do here actually everything in parallel. We make a cold cloud of rubidium and cesium atoms right on top of each other and shine in these tweezers to load them. And we see that they load with very high efficiency. This is kind of typically what you get in these experiments if you don't do anything special. So for us, this was a really encouraging kind of signal that these atoms like to play together, or they play nicely together. There are no kind of unwanted collisions between the atoms. We've also put atoms in other geometries. Here are maybe a little bit more condensed matter-inspired geometries, hexagonal lattices, where we decorate them with single rubidium atoms, or bipartite honeycomb lattices. And finally, we also did like a little picture, a nod to Chicago and its landmarks, the Sears Tower and the Bean. This kind of demonstrates that we have very good independent position control of the atoms. But we were also now quite encouraged by the fact that they seem to play so nicely together if we can do something more. And this is now an idea that we had to start to address this atom loss problem. So here's overcoming atom loss part 1, where we realized what we call a continuous mode operation. And here's kind of a pulse diagram of what it is. You don't have to go into details too much there, but what we basically do is we hold one array, let's say rubidium, while we make a cold cloud of cesium atoms on top of it, and then load the cesium tweezers. And then we can let go of the rubidium array or refresh it, make a cold cloud of rubidium atoms, and then load our rubidium tweezers. So basically we go back and forth from having rubidium in the tweezers to having cesium in the other tweezers. And by that, we can actually ensure that we always have atoms in the tweezers. So here you see over a really long time stretch, we basically indefinitely go back and forth, that we can guarantee that we always have atoms, half of the time rubidium or half of the time cesiums, ready to do experiments. This kind of a nice first demonstration how you could possibly overcome these atom losses. But there's also a second part to it, and that is the question, what actually happens to the coherence of the atoms? Can you keep coherence while you do these reloading processes? As Lindsay said, we want to leave some time for questions in between. So if you have any questions right now, now would be a good time to ask them. And here's also a little Christmas theme or holiday theme tree and snowflakes that my group made in the lab. Again, atom rearrangement and single shot images, really special.
Very, very cool images. Yeah, so there's questions here, and going back maybe to the historical outlook a little bit. One question is, do you think the community will move back to using optical lattices in addition to tweezers to realize larger arrays, or are tweezers just the future?
No. I don't think that this is has to be the ultimate, and there are some really exciting approaches, for example, in the group of Adam Kaufman, where they actually now combine tweezer technology with kind of these lattice technology. So I think there are some real interesting hybrid options, and especially when it comes to maybe very, very large arrays, I think optical lattices could play an important role.
And sort of related to that is a question about what is the minimum separation between the atoms? Could you somehow get things closer together using tweezers that could be advantageous?
Yeah, so in our case, maybe typical separations are a few micrometer, and maybe you could get them even closer. For us, this is a very comfortable distance, because these Rydberg interactions, they can be really tens of micrometers, so you can get a lot of kind of connectivity or interaction range there. But also other groups, actually, they are interested in bringing them closer, potentially even see tunneling between the tweezers. And that is also possible. You have to be a little bit more careful how you create these tweezers, but you can indeed also bring them closer.
Thank you. There's lots of questions here. I get to pick and choose a little bit. Is there, going to the numerical work that you did on the compilation, is there a simple way to understand why the number of gates needed sort of saturates at this 3 to 4 number?
Yeah, I think the 3 to 4 number is kind of, I think, where you see that now you kind of lose that you can do gates over longer ranges. Basically, you save because you don't have to do many swap operations to bring them close. But now you can't do many gates in parallel anymore. So now like everything gets longer, and there's no efficient way of compiling these anymore.
And sort of related to these graphs, in those graphs, there seem to be some small blips, you know, in the higher numbers. Is that just a numerical artifact, or is it
I think those are numerical artifacts, especially, sure. I guess, as the kind of interaction range kind of reaches the maybe 10 by 10 size or so, then there are maybe some artifacts happening. Yeah. But yeah, all the code is available, so you can actually play with that also yourself.
Okay, maybe moving on to the more specific part of your work. There's actually kind of a fun question. Is your optics table really as uncrowded and uncluttered as it looks in this image, or is that old?
No, that's a great question. Okay, maybe it looks a little different now. We added quite a few more beams. That time we didn't have Rydberg beams on there yet, and yeah, it's a little more crowded, but we try to keep things quite neat and tidy. And yes. No,
I mean, yeah, just from a BC person perspective, these systems are so beautiful in that there's just a simplicity to them that you skip some of these steps. I think it makes it really nice. Maybe the last question for now, in the single shot images that you showed, your imaging fidelity for rubidium looks higher than for cesium. Is that real? And if so, is that fundamental or just a technical artifact of your images?
Oh, wow. Okay, then somebody had a very careful look. Indeed, I mean, we often think about cesium imaging a little bit. It depends on at which trap wavelength you are. It can happen that the excited states are quite heavily anti-trapped. So you can run into some difficulty there where you have to choose your parameters a little bit more careful, that you're not just heating out the atoms or so. So indeed, maybe the cesium imaging, at least at these wavelengths where we are working, is a tiny bit more challenging.
Okay. That's all very good. I think I'll let you continue with your talk, and we'll have another pause in a little bit.
Yeah, excellent questions. Thanks so much. So now we still continue with the dual species array, but I wanted to show or highlight one specific result from earlier in the summer where we really use these arrays to do something, yeah, I would say useful and something really new that I think also could be adapted in other communities and can be very helpful. So what we do here is basically that we perform a protocol that allows us to correct for correlated errors between our one species and the other species in real time. So these protocols, sometimes they are called spectator protocols. And what these spectator qubits are, they are basically qubits that are co-located with your data qubits. And you use these qubits to sense the noise environment, maybe environmental magnetic field noise or even control noise that you add into the system. You use the correlation now between the co-located spectator qubits and data qubits to estimate what the error on the data qubits would be, and you actually perform a real-time feed-forward operation to correct for these errors. So I think these protocols, they are really kind of attractive because they allow you to mitigate correlated errors. So these are errors I would say, where error correction can run into challenges. And actually, I don't want to say that this is now replacing error correction. I certainly think we should do quantum error correction, but maybe this could be something that works in combination with it. It allows us to take care of correlated errors and overall maybe just raise the fidelity and maybe raise us above the threshold that we need. So there have been really interesting proposals on these Spectator protocols, but so far there has not been any experimental realization. And I think this is due to the requirements that are actually pretty challenging in these protocols. So in order for this to work, you have to perform mid-circuit readouts on the Spectator qubits without decohering your data qubits. You have to have fast measurements, and okay, fast is always kind of relative to maybe your coherence time, and to now be able to analyze these measurements and do the real-time processing and feed forward. So we were thinking, can we implement such a protocol and do something good for these data qubits in our atom arrays? So here is our implementation of it. Obviously, we are using rubidium and cesium atoms, and now we are also using now hyperfine states to encode qubits in both of these species. And as for the optical wavelength, also these microwave transitions, they're of course completely different for rubidium and cesium. So we can independently drive them by just shining in our microwave horn and tuning either to this or to both frequencies at the same time. So we have independent control and also potentially readout of now the qubit states. And this is actually what we wanted to characterize a bit more, the readout. So in order to do that, let's make it a little more interesting. So here we just drive Rabi oscillation of the qubit states. And now we are going to do decoupling sequences. So basically echo sequences. Here's an XY8 sequence on the rubidium atoms. So whenever you see blue pulses, it's on the data qubits, the rubidium atoms, and yellow pulses and data will be on the Spectator qubits. So if we do this decoupling sequence and we measure basically how much coherence we have left after all these pulses, and we do that by sweeping here the phase of the final pulse and looking at the contrast of that measurement. So for each point here, we basically fit here this phase oscillation curve, and we can deduce our coherence time in this decoupling sequence. We get pretty long coherence, as you see, approaching basically a second. So now the question for us was, what happens to this coherence time when we also perform a readout or maybe even perform some of these pulses on the Spectator qubits? So here we do also dynamical decoupling on the Spectator qubits, and then we read them out. And just to be sure or to really check, is there any effect, we actually keep the readout light on for the rest of the sequence. And now the data I'm going to show you is for the data qubits. So we want to see what is the effect. And you basically see here that there's no effect at all. The rubidium atoms, they don't care what we do to the cesium atoms, and they don't care that we shine in all this light, which also kind of is all around the rubidium atoms, but of course at a very different frequency. So we see that the coherence time with and without performing this mid-circuit readout of the Spectator qubits does not change at all. And when you think about it, maybe it's not too surprising, and it's because of this large frequency separation. And if you just put in from kind of off-resonance scattering, basically, and you calculate what would be the chance of accidentally flipping a rubidium qubit by reading out the cesium atom, and we do a 15 millisecond readout, you would see that this accidental bit flip would be on the order of 10 to the minus 11. But of course, this is purely theoretical. It's important to check this. And here we were really encouraged by seeing that indeed we don't see any decrease. And now actually, because we are doing all of this to the cesium qubits, and we actually perform this readout, we have all this additional data. So we can look at, and this is from the same experiment, how good is our readout of the cesium qubits? So how good can we disseminate bright states from dark states? And we see that we can do that with about 99% fidelity. A mean fidelity. And we also see the coherence time after this decoupling. You see the coherence time is somewhat shorter. This is simply because the decoupling sequence is shorter, and also the trapping wavelength for cesium is closer to the transition, so we get more kind of differential light shifts from that. So the coherence time of cesium here is shorter, but we could surely fix that with longer trapping wavelength. So now let's see if we can do something useful and perform this noise correction or this error correction protocol. So for that now, we do the same thing to the rubidium atoms. We perform an XY8 sequence with a fixed time now. We do this for about 150 milliseconds. And after this 150 milliseconds, we check what is the coherence. And what we do is we inject noise now. So to our magnetic field coils, we inject noise at a fixed frequency, but with a random phase. So in each shot of the experiment, we have a different phase of the noise. It's completely unknown to us, and we have a fixed frequency and amplitude. Of course, you could say, okay, you are doing dynamical decoupling. This should be really good to protect you against noise. That is true. However, it's only true in certain kind of frequency ranges, and there are actually frequency ranges or bands basically where you are very sensitive to this noise. Basically, when you are commensurate with these decoupling pulses, you can very efficiently couple in. And then indeed, we find after this 150 milliseconds that we basically in this protocol lose all the coherence on our rubidium data qubits. However, we can now perform this mid-circuit readout and use the cesium readout to estimate what phase has acquired on the data qubits. And if we then estimate that phase and perform the feed-forward operation, we can, okay, and this is here in the pulse diagram, we do the decoupling on cesium, perform the readout, analyze it on a computer, and feed back to this final pulse, to the phase of it, then we can actually regain the coherence. So here we regain coherence by performing the feed-forward and using this mid-circuit readout of our spectator qubits. So this is the result, and now going a little bit more into the details. Of course, we have looked at different frequencies. How well do we correct for it at different frequencies? So here you see a frequency sweep. Here, this FAC is this frequency where you couple nicely into the dynamical decoupling sequence, so where you're maximally sensitive. And this is basically the data point I've shown you in the slide before. But also at multiples or odd multiples of these frequencies, you would couple into this dynamical decoupling sequence and you are sensitive to the noise. At other places, you decouple pretty nicely, and then actually performing the feed forward, because you do a little bit of additional things, reduces the contrast or leads a little bit to errors that I will also discuss. Further on, here we swapped now at this point the amplitude of the noise, and you see actually here, maybe for the experimentalists, so this is milligauss. So these are almost like typical noise sources that people fight with, at least we in the lab fight with. Actually, just anecdotally, when we first started using this protocol, we didn't inject any noise, and we saw how our spectator protocol was making things better, made us realize that we didn't have the best sources for our magnetic field coils, and then we fixed that noise, and okay, then we had to inject noise, but this allowed us to really carefully characterize this here. We also have a simple numerical model that really nicely captures the features of the protocols. Also, we did a simple estimate or analytical estimate how the fidelity of the protocol scales. And here you see the expression with all these different factors. This is what the factors are. So maybe there are some things that you would expect. It scales with the sensing time. So what is the ratio of how much time do we let these phase errors accumulate on the spectators versus the data qubits? Scales with the sensitivity. So basically, how sensitive are the states you choose between your spectator and data qubits? But importantly, it scales with the number of spectators here. And it also scales with the contrast, basically the measurement contrast on your spectators. And just kind of putting in those values, we get exactly kind of the reduction that we see here. So the main contributor here is actually our finite number of spectator qubits. We just perform a single shot readout on about 60 of these atoms, and then you get, of course, some projection noise. But now having this expression also really shows us what we should work on to make this better in the future. So possible improvements obviously would be to increase the number of spectator qubits. And actually, this is really encouraging. If we would increase that to about maybe 160 or more, while we also increase this readout contrast a bit, then we would actually be able to basically close the gap here between green and blue. So without too much improvements, we could actually here be in a regime where it basically always helps to do this. And other things we are working on improving is the readout speed, using more sensitive states on the spectators versus the data qubits, faster control. Instead of microwave, we would like to use Raman. And then actually, if you were in this regime, you could then even probe more interesting things like spatial dependence, or maybe correct for common mode noise. So this is kind of, I think, a really nice application of this dual species array, but I think it can also really be helpful in other architectures. I promised you that I would come back to this overcoming atom loss. So this is now part number 2. So the question could be, in this continuous mode operation that we did, can we actually keep coherence in one array while we reload the other? And again, okay, that is quite a challenging task. Maybe the light is okay, but as we have seen from the readout now, but you also need all these magnetic fields. You need maybe to make a gradient to load a magneto-optical trap. So can you keep your coherence in the other array in your tweezers while you do that? And one idea we had to basically ensure that we don't get killed by the gradient is basically that we perform a stroboscopic mod while we perform these reloads. And when we do that here, you see basically in blue, the coherence of our data qubits, and in yellow or darkish yellow, you see how many spectator qubits we reload. So you see, we can indeed make a magneto-optical trap in this stroboscopic sense without losing too much of the coherence. The dashed line is without performing the mod, just the coherence of the data qubits without performing the reload of the spectator. But okay, we get a little bit of reduction. Actually, our magnetic field coils, they are somewhat slow, and we could also fix that. I'm quite confident we could actually close that gap. And that's actually really kind of attractive then to get basically fresh qubits into your system. While we were doing these experiments, my students and postdoc, they actually also played with basically leaving out the magnetic field completely. And here actually, this was really interesting for us to see that we could actually just load atoms from PGC, or basically from the stream, from this atomic beam from our 2D mod. We just put on these PGC cooling beams without applying additional magnetic field gradients. And then you don't lose any coherence. You still get a decent number of atoms. And by now, actually, we already improved this a lot, and we have much larger beams to actually hopefully also get like the full loading fraction of 50 to 60% in this approach. So this is actually really nice. So we can reload and keep coherence. So just 2 words or 2 slides on what is next. Of course, for us next, okay, we have a lot of things to do on the Spectator protocols, but what we are now heavily working on is to go to, of course, the Rydberg states, get interactions between rubidium and cesium. And here the story is basically as you would expect it. If you excite rubidium to highly excited states, you get these very strong dipolar interactions. If you excite cesium to these Rydberg states, the same. Question is, what happens? Do you get interactions between them if you excite them both? And indeed, you would get that. Here's a little just numerical calculation. Also, this is all very nicely described in these review papers. So you can be in a situation where everything is kind of the same. You can decide if you just rubidium interacts, just cesium interacts, or you also have these interspecies interactions. But there's actually more to the story. And that is that you can also choose very, let's say, asymmetric interaction regimes by working close to so-called first-order resonances. And here's an excellent paper from Mark Safman on this, which basically gives you a little recipe on how to find these first-order resonances. And there you can have these first-order resonances between the species, giving you strongly enhanced interspecies interactions relative to these inner species interactions. So this is really interesting. And I think there are many protocols that we are interested in where we want to use them. For instance, you could think now in this asymmetric interaction range, you could have one central rubidium atom that controls many cesium atoms around it. And then you could use that for very efficient, let's say, entangled state or GHZ state preparation. This is also kind of inspired by these protocols. Here, you can read more about that. So gives you kind of access to new control mechanisms. The second thing that we are really interested in is now actually not just performing independent readout of rubidium and cesium, but actually using cesium as the auxiliary qubit to learn something about the data qubit. So we perform operations between them and then perform the readout. And why stop at one data qubit? You could really then map kind of the state of multiple data qubits onto the auxiliary qubits. And we are very interested in kind of implementing stabilizer measurements. And then also kind of with the techniques that I have shown you now, kind of these feed-forward techniques, actually then perform feed-forward operations based on these readouts. So where are we? What is the current status on that? Well, earlier this year, we did have first Rydberg-Rabi oscillations on cesium, and we were very inspired by that. And the next part of the story is lots of laser troubles. And I think some of the community can relate to the kind of laser troubles. But I think now we are really on a nice track again, and soon I will show you more Rydberg data, especially here in these first two categories of the interspecies interactions. And I think this is another good point where we could maybe stop for some questions. And here's now the most favorite emoji that we have in the lab, also done in single shot atoms.
Very cool. Yes, thank you for all of this part of the talk. There's a question that you mentioned at the beginning that the spectator qubits aren't necessarily going to replace error correction. Can you comment on when you might want to use one versus the other? And the last part of the question is, are there circumstances where spectator qubits will work better than error correction?
So actually my point was you shouldn't use one or the other, you should actually use them both. I think that's the best. So I think error correction codes, maybe like surface codes, they tend to face challenges when the correlation length of your errors is very large. And this is where now these spectator protocols can come in and help you. They will not be helpful, for example, with bit flip errors. That's what I've shown you are kind of phase accumulation errors. But if I have random bit flip errors, the spectator protocol is not going to help you, and you do need maybe the surface code to help you with that. So my pitch would be use both.
Very good. The other questions are a bit more technical and a little bit related. I think you answered a little bit of this, but a question came up early, which is what is the limiting factor regarding your very good microwave coherence?
Yeah, the limiting factor. So right now, I think so we did see kind of a good increase in coherence time with the number of decoupling pulses. So here we stopped at XY8 or so, but other groups have done hundreds of pulses. What was limiting us in our case is that we didn't have so much Rabi frequency. So right now we are upgrading to a Raman laser system that we can do much faster and much more pulses also. Okay,
that was related to my part of that question, which is, moving to Raman, you always are going to have spontaneous emission enter the picture. Is it just that you can get so much more power that you don't care about that, or?
Yeah, hopefully we want a lot of power. And
okay. So I actually don't see any more questions right now. So let's maybe hear the rest of your talk, and we can leave some time at the end to.
Yeah, great. Okay, questions. Excellent questions again. And so now let me continue. And now I'm going to switch a little bit from scaling the number of qubits to scaling the distance between the qubits. So also kind of historically from my PhD, I'm hugely excited about quantum network applications. And I do think even though now we can maybe scale these systems to hundreds, soon we will see thousands of qubits. At some point, okay, you run out of field of view, you run out of, I don't know how many lasers you can fit into these microscope objectives. So you want some means to connect arrays over a distance. And of course, the beautiful thing about atoms is that they emit photons, and we can use these photons to perform remote entanglement generation between distant atom array nodes. So this is on the mind of many people now. So here the first examples, there are two theoretical proposals. Here, Mark Safman also kind of considering dual species architectures now within the cavity allowing you to efficiently collect these photons emitted by the atoms, and then you would collect these photons and interfere them and measure them, and that would set up your remote entanglement between these nodes. Here in this work, together with the group of Jay Covey, what we looked at is what would be the benefit of it. Now you're not just having a single atom here and a single atom over there, but you have many atoms, so you could actually run many entanglement attempts in parallel. You could multiplex your entangling operations, and that would actually give you a massive boost in the entanglement rate. So here we go up to maybe 100 or 200 atoms, and this is just a single atom, and you basically see order of magnitudes improvements in the entanglement rate. So I think this multiplexing will be very important for quantum network applications soon. And I think it's really timely to think about this now. We see experimental platforms that are realizing optical tweezers in cavities, for example, here in the group of Dan Stamper-Kern. So I think we will soon see really important results here. Another way to interface now arrays with optical cavities is actually to use very small cavities. So here we have large one, maybe near concentric cavities. Could also think about nanophotonic crystal cavities. And then here's a result from Misha Lukin's group, where basically the cavity was used to create entanglement between atoms, and then you can move the atoms from this cavity and preserve the entanglement. Actually, this coherent movement of atoms is now really exciting topic with a wonderful result from Misha Lukin's group, more in the kind of quantum processing area. But I think these ideas can be translated to these quantum networks, and also a wonderful result from the same group on actually implementing also Rydberg operations away from the cavity. So I think this is really an interesting prospect for now combining arrays with even local processing with these optical links. In my group, we are very excited about that, and we also follow the approach of using now the neutral atom as our building block, and then using nanophotonic crystal cavities. And then what you do, how you combine these two things, is basically you use the optical tweezer and you move the optical tweezer onto the nanophotonic crystal cavity, where you can get strong interactions between them, strong coupling, and then you can have a very efficient light-matter interface. What we do a little differently, we want to go very far with this remote entanglement generation. And if you're serious about kind of distributing these entanglement protocol, where you couple your coherent ground states to these excited states in the two-photon process, then you get the telecom photon out, and then you quickly and coherently bring it back to the ground state. So you start off by making a superposition of your qubit, your atomic qubit in 0 plus 1. You take one part of the superposition on this round trip, get half a photon out, then you flip the state around and take the other part of the superposition on a round trip and get the second half of the photon out. This would give you this entangled state where the atom is entangled with the emission time early or late of this telecom photon. So we went into a lot of detail to analyzing this protocol, if this would give us quality entanglement. Okay, there are too many curves to follow here. Up here are basically the optical pulses we do. But down here, I just want to draw your attention to the blue line. This is the population in the 0 state. And you see, as we perform these pulses, we take the atom on a round trip. It goes through all these other states, and in the end, it comes back in the 0 state. And basically, the fidelity or the error that we have is basically how much do we come back in this state. And maybe not too surprisingly, the error here scales with the cooperativity. So how strongly do we couple to the cavity? So here you see an analysis of that. Actually, for values that have already been realized, not even working at telecom wavelengths, but at infrared wavelengths of about close to 100, you can expect that the error could be maybe on the percentage level. So this motivated us hugely to actually make this happen, and I'm excited to show you our progress towards that. So here now, away from cartoons, here now you see real nanophotonic crystal cavities that we are making in collaboration with Alan Debos at Argonne National Lab. So these are silicon nitride photonic crystal cavities. They work at the telecom wavelength, and that is actually really nice, because suddenly working at longer wavelength, as opposed to maybe infrared, you're less sensitive to all maybe imperfections. And we got really nice quality factors, and also kind of at the wavelengths where we have these transitions in cesium. These are the cavities we have now. Actually, here in the SEM, you see that the cavities, they're basically suspended from a chip, but on the other end, they are not suspended anymore. They just kind of point into free space. And this is actually the architecture that we have. Because what we want to do, or what we are already doing, is that we couple to these cavities from free space. So we don't attach fibers to it or have grating couplers or any of that. We just have the freely suspended cavities, and then we basically launch the photon from there. And we have engineered or designed the taper of the waveguide to basically have this outgoing mode match nicely to the coupling mode of an objective. So by just looking at the overlap of these modes, numerically, we would expect to maybe get up to 90% coupling efficiency. So this is hugely encouraging. And also the group of Jeff Kimball has seen also experimentally really encouraging numbers, but we also wanted to see it for ourselves. So here you see image of our characterization setup with one of these chips in here with these freely suspended cavities. Here's another nice SEM image. So they really just launch out of the chip. And then we couple to it and characterize the coupling efficiency. So this is now experimental data. Okay, it doesn't go up to 90%, but it almost goes up to 60%. And there are still many knobs to turn. And 60% is for us already hugely encouraging. And I would be already really happy for the remote entanglement generation with these numbers. But we think we can do even better. Now we have the chip, we have the free space coupling. Let's put it all together. So here's another neat setup. So this is actually, this picture was taken yesterday. So this is actually what the table looks like right now. Very neat. And the reason why it's so neat is actually we recently just opened up the chamber and put the photonic chip in. So, and this is what it looks like now. And this is actually from before we put the chip in, we have an atomic array also in this setup, a bit smaller array, 4x4, but this is already yeah, really exciting. But now if you look into the chamber kind of from that direction, you indeed see, so this is also where the microscope objectives go in, but now they are out, and you see the chip here. And yeah, the chip, the big advantage here is really that you have many, many of these cavities that now launch into free space. So here just a little cartoon that kind of fits maybe to the angle of this. So the chip sits inside, the photons will be then collected with the photonic crystal cavity and then emitted into free space. And then from this direction, we come with our coupling objective or lens. So the features of this setup is really that the atom array is integrated from the start. We have the free space coupling, can have many cavities, and then you can even think about like moving multiple atoms to multiple cavities and then doing this sort of multiplexing that I discussed. So what we are now feverishly working towards is generating these entangled states. And there's a very nice perspective towards like real long distance distribution, and that is that here in the Chicago area we have kind of a unique infrastructure. We have these dark fibers between UChicago, Argonne National Lab, Fermi Lab. There are actually a few more nodes here in the Hyde Park area. So it's kind of a real nice network testbed where we can now hook up different quantum systems. And we have actually one end of the fiber going into our lab. So once we create these states, it wouldn't be any problem, or okay, there will be lots of problem, but wouldn't take much to just send them down this fiber and then detect them at Argonne National Lab. And then if you think about like what would be entanglement rates over such distances, these are kind of some conservative estimate. I would expect to have a remote entanglement rates between 2 atomic nodes over these distances on the order of 10 Hertz. And that might sound slow to some people. Actually, this would be a record fast, and this would be by far the fastest and the furthest entanglement generation to date. In this kind of network stream, we also have a lot of other projects going on. We have a hybrid project going on where we couple basically the light that comes out of these atomic states and couple it to a solid state quantum memories in Tian Zhong's lab. We found basically a very lucky coincidence that erbium rare earth ions in his crystals are basically on resonance with our rubidium atoms. So we can just send them over, and we have fibers between the labs. And then we are working towards really integrating everything, the atom arrays, together with these photonic links. Lastly, I want to draw your attention to this map again. This is actually from my Google Maps. So you see all these little flags. They are places of interest that I find very exciting. Chicago is a really exciting town. If you are ever in town, please reach out. I'd be happy to show you the lab. And if you were to come to the lab, you would meet an amazing group of people. So I really owe all these wonderful results to this amazing group of people. And yeah, I thank these people. I thank you very much for your attention, and I'd be happy to answer more questions.
Thank you very much for a really exciting talk and some really beautiful results. I'll again encourage the audience to please ask questions with the Q&A tool in Zoom or the YouTube chat. But we do have a couple in the queue here. So one is, it looks like you have some pretty hefty coils on the apparatus for the atom cavity project. Are those required specifically for the 4-wave mixing scheme you're using, or are they just mod coils?
They are actually just mod coils. Yeah. So here, like, yeah, we tried something new. All the setups that I previously worked with, they were all with glass sets, and glass sets allow you kind of a lot of optical access, and you get the coils a little bit closer. Here it's a steel chamber, which now has the added benefit that we have lots of mounting options for our photonic chips, but it puts the coils a little bit further away, and this is right now what the dimensions are. I think there are some opportunities to bring them closer, or I know other groups are even putting the coils into the vacuum chamber. So I think it's not real fundamental, but this was for us maybe the most convenient right now.
Sure. Another question was, when you have such high Q optical cavities, how difficult is it to match these resonances of the cavities with the atomic resonance? Is there any way to tune that resonance?
Great question. Actually, this is a question that's now very much on our mind. So actually, initially I would have said you definitely need a tuning mechanism. You need to bring the cavities on resonance. Of course, you need that. And okay, we are thinking thermal tuning, sending in another laser beam to kind of heat the cavities and tune them. But we're actually finding now, because we have so many cavities in there, that there's actually a pretty good chance that we might just find a cavity that is on resonance without us doing that. And also talk with other groups that are very confident about fabrication capabilities, and they say you can just fabricate them on resonance. I'm not super convinced, but now having a range of resonances might make this actually quite feasible.
Okay. So can you tune the atoms instead, or is that?
Oh, can you tune the atoms instead? I think not by the amounts you would potentially need. So maybe in previous experiments, we tuned by a nanometer or so. That would be tough for the atom.
Okay. Another question, I mean, maybe more bigger perspective. I mean, you've worked on different kinds of physical systems in your career. Are you really sold on atoms these days, or what do you see in quantum networking in particular is sort of, you know, what is the best physical system out there?
I mean, first of all, I enjoy working with all kinds of systems. I really love kind of seeing the same quantum effects kind of in different systems. So I don't so much think of it as a competition. And I would actually say now through discussions, I mean, we learn a lot from maybe the NV Center crowd and actually in my group, there's a large NV Center networking representation. Actually taking those ideas now to the atoms, I think will really help the atoms to push forward. I do think there is something to be said about atoms, that they are simply all the same, and it's something that is really different with NV centers and tough to realize. So while we are now maybe struggling with things where NV centers, okay, they are just trapped there and you don't have to think about the trapping. I think trapping now for atoms with these optical tweezers has become so much more convenient and kind of available, that now we can really focus on the networking task and then leverage the fact that we have many atoms.
Yeah, I think you're speaking to the choir here, but it sounds like very convincing to me. So
It's not too difficult at Vamos.
yeah. No, yeah, the indistinguishability of atoms is one of these beautiful properties that I think is sort of underappreciated, but among
Yeah, we take it for
ones.
granted, but
Yeah.
that's why, I mean, sometimes I like to say in my PhD, I spent like 2 years just trying to make two NV centers the same so I could entangle them. I mean, here you just get it for free, and yeah, that's really amazing.
Yeah. One last chance for questions. Anybody? All right. Well, if not, thank you so much for really interesting talk and for coming with us this late date in December. For the audience, the next talk will be on January 20th. We'll resume in the new year. And so we hope to see you all then.
Awesome.
Thanks,
Thank you.
everybody.